Hello students, in this section we will continue our Boolean algebra. In our first class or last class we have discussed about the what is Boolean algebra, and here we will discuss about the example. So let's take an example. This is the example. Here our question is, let B plus dot be an algebraic structure and plus and dot are two operations for the set B which is contain the element 0 and 1. We know Boolean algebra contains only two elements, that are 0 and 1, and these are the two tables that is defined here. For plus 0 plus 0 equal to 0, for 1 plus 1 equal to 1. Similarly these are for multiplication also similarly this. So we have to prove that the set B with defined binary operations is a Boolean algebra. These are the two tables which is given and our algebraic structure is this. So we have to prove this B is a Boolean algebra with this condition. Okay, so let's start to prove. First property is our closure property, and by this table we know that every element of this set is closed with respect to the binary operations. And commutative property is A plus B equal to B plus A, or A dot B equal to B dot A. So here from these two tables this satisfies the commutative property. Next, the associativity property. Associativity property, we need three elements. So here only two elements is present, 0, 1. So you can take another element, that is 0 or 1. So for the additive 1 plus 0 plus 1, that equal to 1 plus 1, and this equal to 1. Same here, 0 plus 1, that is 1 plus 1 equal to 1. Consequently this and this two value are equal. This satisfies the associativity property of addition. Next, similarly we have showed here for the multiplication. So the associativity property is satisfied for addition and multiplication. Now the distributive property. So in the distributive property we have shown here, these are the property 1 plus 0 dot 1, this equal to 1 plus 0 equal to 1. For this 1 plus 0 dot 1 dot 1 plus 1, that is equal to 1 plus 1 equal to 1. So here these two equations satisfy the distributive property. In first, plus sign distributes over dot sign, and second, dot distributes over plus. These are the operators. Next, identity law. Identity law says this 0 plus 0 equal to 0 and 1 plus 0 equal to 1, that is equal to 0 plus 1. Therefore 0 is the identity for plus operation. Again this 1 is the identity for dot operation, which is unique identity exists for both the operators. Again, complementation law. Here complementation law for 0 plus 1 equal to 1, which is equal to 1 plus 0, and 0 dot 1 equal to 0, that is equal to 1 plus 0. Therefore 1 is the complement 0 for both the operations. Also this, so 0 is the complement of 1 in both operations. So we got here 1 is the complement of 0 and 0 is the complement of 1. So our structure B plus dot is a Boolean algebra. This is the first example. Similarly we can solve many more examples. Here if S is a non-empty set, then the poset PS of S along with the two operations of union and intersection, such that PS union intersection is the Boolean algebra. We know that operation union and intersection satisfy the closure, associativity, commutativity and distributive property for all A, B, C belongs to PS, that is the poset. Again, null element and the universal set. Null element and the universal set also satisfy the operation, and here ADX equal to U minus A. This is the complement, ADX equal to U minus A. For each element A belongs to PS for both the operations. So this also a Boolean algebra. Similarly for the set of operations conjunction and disjunction, we can also prove this is a Boolean algebra. So now let's take, this is the D24 series. Here this 1, 2, 3, 4, 6, 8, 12 and 24 divides 24. If we define the plus and dot operation here in D24 as A plus B equal to LCM of AB and A dot B equal to GCD of AB, and A complement is 24 divided by A, because the divisor is there, so we have to divide here. For any A, B belongs to D divided by 24. Then we can prove this D24 is also an Boolean algebra with identity 1 and U is the 24. So 1 is the unit element and 0 as the 0 element. We have taken the 0 element, that is 1, and the total element, that is 24. So D24 is also a Boolean algebra. Now the relationship between Boolean algebra and lattice, we have already discussed about that. A complemented distributive lattice is called a Boolean algebra. So now let's take an example of this. Okay, from the very beginning, this example. This is the example. Okay, this is the Boolean algebra of set, then a set, B process other, then according to this theorem, A is subset of B. Okay, so we can show this all also. So let's take an example here. Similarly, we have discussed about this. So LCM of AB is equal to B. This is the set 1, 2, 3, 4, 6, 8, 12 and 24. This is the Hayes diagram using the post set. This is a Boolean algebra if this condition is satisfied. What is this? Is the complement of 1, 24, 24, 1, and this is a distributive lattice also. So this is, according to our lattice, we can prove this is a distributive, this is a Boolean algebra. Okay, sorry. Okay, now let's take the theorem. If an integer n can be written as a product of r distinct primes, means n equal to p1, p2 to pr, then p1, pi's are distinct primes, then the lattice dn, the divisors of n under the operations or meet and join, this is the meet and this is the join, is a Boolean algebra. This is our theorem. So using this theorem, we have discussed about this example also. Okay, here let's D33 is the Boolean algebra across 33 equal to 3.11. Because 33 is equal to 3.11, these two are prime numbers, so D33 is a Boolean algebra. D105 is also a Boolean algebra because 105 equal to 3 into 5 into 11. These all are prime numbers. For similarly 70, 257, for 40, 2225, and 2's are not distinct here. For 40, 3 2 are there. Here 257 all are distinct, but here not distinct. So D40 is not a Boolean algebra. Similarly for D75, 3 5 5, 5 is not distinct. So D75 is not Boolean algebra. So now let's discuss about sub-Boolean algebra. A sub-Boolean algebra means, first of all, a Boolean algebra is given. If a set is given, then its subset must be a sub-Boolean algebra. If let B be a non-empty set of B, this is a Boolean algebra with 0, 1 as identity element for the binary operations plus and dot respectively. Let Bdex be a subset, non-empty subset of B. So if Bdex contains the elements 0, 1 and is closed under operation plus, dot and complementation, then this Bdex plus dot complementation or this total Bdex plus dot complementation 0, 1 is called a sub-Boolean algebra or sub-algebra. It is evident that Bdex itself must be a Boolean algebra. To check Bdex is a Boolean algebra, we need either one complement of this there, either one of the set operation plus or complement, or dot complement only. It means BDX is closed under plus and complement or under the operation dot and complement, then it is a sub-Boolean algebra. This is possible due to some properties, and the properties are: for all AB belongs to B, A plus B equal to ADX plus BDX complement. Means A complement dot B complement whole complement. This is the our complementation property. So using here only one we have to prove. Note that the subset 0, 1 and the set B are the sub-Boolean algebra. This is the one Boolean algebra. The set A ADX 0, 1 where A is not equal to 0 and A is not equal to 1 is a sub-Boolean algebra. The Boolean algebra is this. Again, a subset of B generates a sub-Boolean algebra. So let's take a theorem. If two subset are Boolean algebra, if two Boolean algebra are there, then intersection of there is also a Boolean algebra. So let's take here S1 S2 two sub-algebra of a Boolean algebra 2. Then prove that S1 intersection S2 is also a Boolean algebra of B. Here we have to prove S1 intersection S2 is closed with respect to the operation plus complement. That means let AB belongs to this. This implies AB belongs to S1, A plus B belongs to S1, AB belongs to S2, A plus B also belongs to S2. This implies AB belongs to this, so AB belongs to this S1 intersection S2. Therefore, S1 intersection S2 is closed with respect to the operation plus. Again, A belongs to S1 intersection S2, so A complement also. If A belongs to S1, implies ADX belongs to S1 because S1 is a sub-algebra. Similarly, if F belongs to S2, ADX belongs to S2 because S2 is a sub-algebra. Hence, we can say that these two equations satisfy that ADX belongs to both S1 intersection S2. This means A belongs to S1 intersection S2 and ADX belongs to S1 intersection S2. So S1 intersection S2 closed with respect to the operation complementation. So S1 intersection S2 is closed with respect to the operation plus the DEX, that is plus complement, hence it is a sub-algebra. Let's take another example is this. This is the figure. This is the algebra. So the following two subsets are sub-Boolean algebra of this. B1 A ADX 0, 1. A, this is the A ADX 0, 1. A ADX 0, 1. Okay. B2 is the ADX dot B ADX dot B ADX B A plus BDX 0, 1. ADX B A plus ADX, this is 1 and 0, 1. So the following two Boolean are all not okay. These two are Boolean algebra and these two are not Boolean algebra. So let's take another example, that is D30. This is D30. Here this is a Boolean algebra because 30, 2, 3, 5 is a product of distinct primes. So this is a Boolean algebra. Again we can take a subset of this, that is B1 1, 2, 15, 30. These all are distincts. 2 prime are distincts. Here 1, 3, 10, 30. These are the distincts. 1, 5, 6, 30. These are also distincts. That's why this is also a sub-algebra of B. Similarly, we can show this. Let's take here also for this thing here. From the joint and mate, we can also say GCD and LCM are here also. This relation less than equal to divides and 0 element is 1. Here we have discussed the example of Boolean algebra and sub-Boolean example. So this example you can calculate yourself and you get through about this. Okay, all the best.